This is a video for AQA Further Pure Mathematics, Matrices, section 3.3, finding the determinant of a 3 by 3 matrix. The process for finding the determinant of a 2 by 2 matrix should be well known to you by now. And what we want to do is to now look at the method for finding the determinant of a 3 by 3 matrix. The first thing to note is that we can find the determinant by using any row or any column that we like. And to work out the determinant, we take each element in a row or column and multiply it by its cofactor and then find the sum of those. So for example, if we're using column 1, in other words A1, A2 and A3, we would find the sum of A1 multiplied by the cofactor of A1 plus A2 multiplied by its cofactor plus A3 multiplied by its cofactor. We refer to this as expanding by the first column. And as I said, we can use any row or any column in the same way. And there are some advantages to carefully picking which row or column that you might choose to calculate the determinant. So using the first column, we get this expression. Using the first row, then we will get this, where these are the elements in the first row, A1, B1 and C1, multiplied by their corresponding cofactors. So let's have a look at this example. And what we're going to do is to find the determinant of this matrix by using the first row. So that will be equal to 5 multiplied by the cofactor of that first element, which will be the determinant of the little matrix 2, 3, negative 1, 4. Remember that you're looking at deleting the row and the column containing the element, and then finding the determinant. The next one will be plus 1 multiplied by its cofactor, which is negative 3, 3, 8 and 4 for the determinant, but we must then apply the sign, which is negative, so this will make this equal to negative of, so we're multiplying 1 by negative of that determinant there. And then finally we've got plus negative 2, which is the element, multiplied by the determinant negative 3, 2, 8 and negative 1. Now if we calculate those, the first one is 5 multiplied by 11, so 8 minus negative 3 is 11. The second one we've got in the determinant negative 12 and then minus 24, it's negative 36, but we want minus of that, so that's plus 36. And then finally we've got negative 2 and multiplied by the determinant, which is 3 minus 16, so negative 13. And if you multiply all of those together, you get the value, if you add all of those together, beg your pardon, you get 117. So the determinant is equal to 117. So as that was expanding by the first row, here's the working for expanding this time by the first column. So you can see that the elements we've used are 5, negative 3 and 8. Remember the signs that we're using for the first column, positive, negative and positive, so hence the negative sign there. But you'll see that we get the same value of 117. Well, you might think it's a little bit strange that it doesn't matter which row or column you use. However, if you to look at this where we're doing it algebraically, you can check for whichever row or column you decide to expand by, then the expression you get is given by this, and it doesn't matter therefore whether you use column 1, 2 or 3 or even row 1, 2 or 3. So it's important then to realize that that is the case. So what we can do is, if we choose carefully, we can save a lot of work, particularly if some of the elements in a row or column were 0, then obviously we wouldn't have any value coming from those elements. So if you can choose at all possibly a row or column which has got at least one or maybe more zeros, then calculating the determinant becomes much more straightforward. So here's a case in point where you can see that we've got a 0 in the second row. So if we choose that row to calculate the determinant by, then the first part is 0. We've then only got two little calculations to do. The element for 3, so its cofactor is given by the matrix 4, 5, 2 and negative 2. So looking at eliminating those rows and columns. And then for the other element, we've got minus because of the sign in our table here, and then 1 multiplied by the determinant given by the matrix made up of the elements which have not been deleted. So looking at that one, we'd be deleting those, giving 4, 1, 5, 1 as our determinant. So the important thing is that the 0 there means that we've reduced the calculations that we need to do, and we get a determinant for that matrix of negative 53. Now, although the methods look quite different for 2 by 2 and 3 by 3 matrices, they are in fact just extensions of each other. Just that for a 2 by 2 matrix, it's very straightforward. However, we're doing exactly the same thing with the 3 by 3, working out the elements multiplied by their cofactors. If you go to 4 by 4, we would have exactly the same thing, but we'd need to find the cofactors for each of 4 elements, and each of those cofactors involves finding the determinant of a 3 by 3 matrix. So you can see how the complexity of finding determinants it builds up. So it's quite long-winded to do a 4 by 4 matrix by hand. Well, here's a question that uses the knowledge that we've built up about the determinants of 3 by 3 matrices. First part says that we need to show that x equals 2 is a root of the equation which is given by the determinant. So quite an unusual way of seeing an equation perhaps, but the determinant equal to 0. So if we want to show that x is equal to 2, we would simply need to substitute 2 into there. So, and that would give us 1, 1, 2, 2, 2, 3, 2, 2, 0. And you could use a calculator to show that that is equal to 0, and hence x equals 2 is a root. Alternatively, we could work out the determinant as an equation. So because we've got a 0 in the final row, I'm going to expand that by the final row, and you can see that it will be x multiplied by the determinant of 1x x3, and then minus of 2 multiplied by the determinant of 1x and 2, 3. And if you multiply that out, we get x multiplied by 3 minus x squared, and then minus 2 multiplied by 3 minus 2x. And that must be equal to 0 because we're told the determinant is equal to 0. If we expand that, you get x cubed minus 7x plus 6 is equal to 0. Now we know that x equals 2 is a root, so therefore x minus 2 is a factor. So taking that factor x minus 2, we must be left with a quadratic x squared and minus 3 at the end, so the middle term is plus 2x, and you can check that quite easily. And that will give you the negative 7x required. And that factorizes, so we get x minus 2, and it factorizes to x plus 3 and x minus 1 equals 0. So therefore the other roots are 1 and negative 3. Well, that concludes this video on determinants of 3 by 3 matrices. In the next video we'll put all of the ideas so far together to show how we calculate the inverse of a 3 by 3 matrix.